Hello and welcome back to Historical Geology. Today I want to talk about Chapter 8, which deals with the Hadean and the Archaean eons, the Hadean, Archaean, and also the Proterozoic. We combine all those into a general term called the Precambrian time. So remember, the Cambrian period is the first period of the Phanerozoic eon, the time of visible life. Remember, phan means visible, zoic is our animals. So we start seeing a lot of fossils, and mainly what happened at 542 million years ago was the development of hard body parts, and life developed shells, and so it's easier to leave a fossil if you have a hard body part. But note that this Phanerozoic eon really only accounts for about 12% of Earth's history from 542 to present, and you'll see that the bulk of Earth's history is about 88% occurs during this Hadean, Archaean, and Proterozoic times. So today we'll be looking mostly at the Archaean and the Hadean. So we're looking at 13% of time for the Hadean and about 33% for the Archaean. And note the divisions here. Remember, there are very few fossils. We do see quite a bit more fossils in the Proterozoic time. Remember, proto means what came before animals. Thinking of the Archaean eon, we're looking at 4 billion years to 2.5 billion years ago. Note that this 4 billion year really coincides to the time where we have the oldest rocks. And you'll find that those oldest rocks are called the Acosta gneiss. And the Acosta gneiss is up in the Northwest Territories of Canada. And it's exposed Archean rocks, and those are about the oldest rocks on Earth. The only thing older than the Acosta gneiss would be the meteorites that fall from space. And so that kind of gives us a number based on, again, an absolute time. And then the absolute time of 2.5 billion years, or 2,500 million years ago, marking the end of the Archean. By this time, we really start kicking into modern style plate tectonics. So that's kind of the division there. But again, it's an absolute age. And of course, 542 million years marks the development of this Cambrian explosion, diversification of life, where life develops these hard body parts. In terms of the Hadean, going back from the beginning of Earth of 4.6 billion years ago, or 4,600 million, to 4 billion years ago. So again, this is really marked by a time of high heat flow, very little to no felsic crust. All we're seeing is really ultramafic and mafic oceanic type crust. We have a strange type of Archean tectonics here in terms of subduction, kind of a strange style of subduction. But really, the other thing that's happening here is we're seeing this intense meteor bombardment, or this heavy bombardment period. What are some of the highlights of the Hadean Eon? First of all, during these 4.6 to about maybe 4.5 billion years ago, we're seeing Earth accrete from the planetesimals. And we've talked about this already when we talked about the origins of the universe and the solar system. By this process of this accretion, Earth is getting larger, the mass increases. Another thing we're seeing is the gravitational differentiation. This occurs between 4.5 to 4.4 billion years ago. And note that Earth started off as this homogeneous sphere, pretty much the chemistry the same in the middle as it was in the outside. But then as time goes on, the heavier elements sink to form the core. The mantle forms. Note that there's really no crust forming at this time, maybe some ultramafic rock, and here we're seeing some meteor bombardment. But eventually we start getting to this stratified Earth. The other key thing that's happening here is that we're seeing this gravitational energy be converted to a thermal energy, so that adds to Earth's heat budget. We also talked about this Mars-sized planet Theia and how it collided with Earth, and some of the criteria for the moon and how it formed. So that happened around 4.4 billion years ago. I mentioned this late heavy bombardment period, and that occurred between 4.1 and 3.8 billion years ago. The other important thing about this heavy bombardment period is that there was a thin ultramafic crust that was starting to form at about 4.4 billion years ago. In fact, there's good chemical evidence for water being forming at this time as well. However, this late heavy bombardment period obliterated that early crust, probably remelted it, and again, the frictional energy from these impacts contributed to Earth's heat flow. In fact, that's where we talk about this extremely high heat flow. the rocks on Earth were anywhere from 3 to 6 times hotter during the Hadean period than they are today. And we had this intense cosmic radiation. That's because during this time, even though the sun may have been only 70 to 75% of its heat radiation, it still gave off a solar wind, which are ultraviolet charged particles that release an intense cosmic radiation. And the magnetosphere is an Earth's magnetic field that would shades us from that magnetosphere. So any form of life that could have started developing on Earth's surface was really obliterated by not just the heavy bombardment of meteorites, but also this cosmic radiation. So life really didn't have a chance during the Hadean Eon. So thinking about this high heat flow, why was the Hadean so much hotter? Well, there are 3 reasons. The first is this gravitational energy. So remember, we have the differentiation into the core and mantle. And so that gravitational energy is converted to thermal energy. Also during this time, in the initial solar system, there were many short-lived radionuclides. In other words, there were radioactive atoms that had very short half-lives. They're pretty much all gone, but they were around back in this early Hadean and Archaean time where they were contributing to Earth's heat budget. So today the main nuclides that are contributing heat to Earth are potassium-40, uranium-238, thorium-232, and to a little extent uranium-235. Remember, radioactivity produces this extra heat. And note that in the Archaean or Hadean 4.5 billion years ago, these radioactive elements do not account for all the heat that was going on. So in other words, this extra heat here is either from that gravitational thermal energy or these short-lived radionuclides. And also remember, all these meteorites and planetesimals were hitting Earth, so that frictional energy contributed to the high heat flow as well. So 3 to 6 times more heat during this Archaean Hadean time. Yeah, heat production 4 billion years ago was 3 to 6 times greater than today. So think about this magnetosphere. Recent work has shown that the magnetosphere, or Earth's magnetic field, really developed around 3.45 billion years ago. And then this magnetosphere, really what it does is that Earth develops a geodynamo. And the dynamo basically are these, as Earth starts spinning, we have this core, liquid iron core, which is rotating, and that generates an electric field. Whenever you have an electric field, you generate a magnetic field. Remember, electromagnetism goes hand in hand. And that magnetic field will deflect that solar wind or those charged particles that emanate from the sun and deflect them around the Earth. This new study finds from rocks in the Craton, and these are some of the oldest rocks on Earth. They're about 3.5 billion years old, about 3 billion years old. Really one of the first continental landmasses that started developing. And it concludes that this magnetic field was 50 to 7% of what it is today. But they find that that's actually strong enough to deflect that solar wind and protect that life that was developing. The other thing we look at are zircons. Remember, zircons are zirconium silicates. Zirconium is about the same size, or at least the site it occupies in the crystal can be substituted with uranium. So we get some uranium. Zircon crystals often contain a significant amount of uranium. And we can use that for uranium lead dating, because remember, uranium decays to lead, and we can use the 2 different isotopic clocks to help us date these rocks. We find that these zircons give us ages of 4.4 billion years for some of the oldest minerals. There are no rocks of Hadean age, but we do have these minerals suggesting that rocks are forming, but they were probably being obliterated probably by those meteor bombardments, or just the high heat would remelt them pretty quickly. So in fact, here are some of my zircons, some of the work I did when I was in grad school. These are from northern Mexico. Thinking about this Archaean Eon, the oldest rocks, I mentioned the Acosta gneiss. Then we had this thin ultramafic crust during this Archaean time, mafic basaltic oceanic crust. We had these detrital zircons. Remember, detrital means that they occur in sediments. So they formed in a rock. That rock was weathered. There was erosion, and that sediment came to rest someplace, and so they're detrital. These zircons there's little inclusions that have water, and that water, when we measure the oxygen isotopes, we find that they're consistent with the liquid water. So there was liquid water on Earth's surface shortly after the formation of the planet. So Earth had cooled enough for oceans to begin to form about 4.4 billion years ago. And then we talked about this biomarker for carbon isotopes, where the photosynthesis prefers carbon-12 over carbon-13. And that dates to 3,700 million years ago. 3.7, your book says about 3.8 billion years ago. So we're looking at, as soon as land masses start forming, water starts forming. And remember, the other big thing, 3.7, 3.8. 3.8 was the end of that heavy bombardment period. Once Earth's not being assaulted by these asteroids and meteorites and comets, life was able to take hold. So here's a picture of the Costa Gneiss, granite gneiss complexes, right, abandoned gneiss, the oldest rock on Earth. So reviewing a little bit about the Archaean eons, remember there's no felsic rocks. That's not going to come till a little bit later on. We mostly have these ultramafic rocks, and remember the lava flows that are ultramafic are called komatiites. We don't really see those anymore because Earth doesn't have that heat budget anymore. Mafic rocks would form that beginning, that proto-oceanic crust. How would these form? So you have upwelling currents in the mantle. They disrupt this ultramafic crust, and by pushing this ultramafic crust around, maybe they're colliding with each other, and you start developing the first subduction zones. And remember, the first subduction zones lead to the first formation of island arcs, sort of like a Japan-style arc or a Tonga or a Fiji, where you're seeing an ocean-to-ocean convergence. During the Archaean time, the subduction was a little bit different. The mafic crust might have been thicker through a process called underplating, whereas this upwelling mantle currents, they reach the surface, they begin to cool, and they kind of cool from the bottom down. And so the crust gets thicker and thicker through this underplating. And then as these currents disrupt this ultramafic crust, they start colliding with each other, converging with each other, forming subduction zones, and that leads to a really shallow type of subduction where it's not, because remember it's still very warm, high heat flow, so it's not going to sink steeply into the mantle. It's going to be a shallow type subduction. Instead of melting the upper mantle, you're probably melting that mafic crust or ultramafic crust. And when you do that, you're going to produce something that's less mafic, that's more felsic. And you'll see that we're going to produce these rocks called tonalite, trondhjemite, and granodiorite sequences. And those are going to lead to the first more felsic rocks, which eventually lead to continents, right? So we're going to weather these rocks, and we're going to produce sediment that's even richer in silica. So this early Earth, about 4.6 billion years ago, molten, maybe a few little strands of ultramafic komatiite or mafic oceanic type crust. Earth was spinning much more faster, 10 hours per day. We had that heavy meteor bombardment from comets and asteroids. No continents, again, that intense cosmic radiation, widespread volcanism. The other thing is that the moon was much closer, so there was a strong tidal force on that water. So again, reviewing here, early Archean crust was probably thin, made up of ultramafic rock, those komatiites. So again, ultramafic rock has less than 45% silica. It was disrupted by these upwelling mafic currents, maybe at the beginnings of mid-oceanic ridges, or maybe mantle plumes that are coming up. And then we start forming this first subduction and island arcs, and we start getting those melting of that subducted mafic rock in particular to produce the less mafic trondhjemite, tonalites, and granodiorites. And then so we're forming that continental crust, these early Archean cratonal rocks that are going to be richer in silica material. And then eventually these protocontinents, these little island arcs, protocontinents, start merging with each other and start growing in mass, and they become larger over time during the Archean. A couple of terms before we look at these Archean cratons. There is a term called a craton, and the craton really refers to the stable interior portions of continents. Usually they're Precambrian rocks, Archean proterozoa. The Precambrian shield is the exposed part of the craton. The platform is a region of the craton that's covered by younger sediment. So here's Phanerozoic sediment that's covering that platform. And remember, the craton refers to this whole region here. So really we're looking at the Precambrian shield, the exposed region, and the platform, which is buried by younger sediments. Looking at the distribution of these Precambrian rocks, just about every continent has them. You can see Africa has quite a bit. Some of the oldest ones are down here in the Witwatersrand and the Katvaal Craton in South Africa. The oldest rocks on Earth are up in the Northwest Territories of Canada, up here in the Costa Gneiss. But you can see much of Canadian Shield is exposed Precambrian rock. Note that we have some down here in the Grand Canyon. You see some of those that are buried under the Grand Canyon sequence. And then we see some over here in the western U.S., but pretty much every continent has some bit of this exposed Precambrian rocks.